Mechanical storage with liquid media is mostly and commonly represented by so-called hydropower plants. These hydropower plants use potential energy, mostly the potential energy of the water of these hydropower plants to generate electricity. So simply put, what is potential energy? Potential energy is simply the energy difference between a higher and a lower position, and a body at this higher versus a body at this lower position. So what we are doing is a simple kind of setup, actually. We have an upper reservoir, which has a higher potential energy if there's water inside than a lower reservoir. So this kind of upper reservoir here is simply filled with water, and it's connected via a pipe which runs through a pump and a turbine to a lower reservoir. Based on the height difference, we now have different potential energies. So let's have a deeper look into the energetic situation here. So the potential energy in terms of physics is defined as the mass times the gravitational acceleration times the height. And because our water up here has a greater height than the water down here, we do have a difference in potential energy, which I can then simply write as mass, because the mass is the same no matter if the water is up or down, times gravitational acceleration, times the difference in height we're having between these reservoirs. Now, the potential energy calculation with the mass is a little bit unhandy. So it is better if we talk about water to define it as a volume rather than a mass. So we can rewrite this equation and say that our potential energy difference between water in the upper reservoir and water in the lower reservoir is the volume times the density of the liquid times the gravitational acceleration times delta H, which is basically the effective drop height of the water when it's transferred from the upper to the lower reservoir. And we have to multiply this by some kind of efficiency value. So how do you operate this kind of system now? Well, when you have an energy surplus, you pump up water from the lower reservoir with your pump and electricity, which is run by electricity from the grid, from this motor. You pump up the water in your upper reservoir and you fill this up. Now, if you have times of high demand and lower production, you let water flow down from the upper reservoir into the lower reservoir, and due to the potential energy difference, you will be able to run a turbine, which in turn runs a generator, which gives or feeds back energy into your electric grid. The power this kind of system can supply is very intuitive here because it's given by the speed of the flow volume. So the power is basically the speed at which you can empty your upper reservoir and flow water back into the lower reservoir. So this can basically be represented to some extent by a flow rate Q, and Q is a volume divided by time. So if we have an upper reservoir which has double the size, then it has double the storage volume. So we can store twice as much energy in there. And if we flow this down, this takes a certain time. And this is what the power will express. Basically, how fast can we empty our upper reservoir? So if our upper reservoir is doubled and we can still empty it at the same time, our power doesn't change. However, if we have our upper reservoir at a fixed size and we double the size of the pipe which is going to the lower reservoir, then you can empty the upper reservoir twice as fast as before. So I want to have a look at each of these contributions to our delta E pot, so our difference in potential energy, therefore our basic storage, energy storage, and at the power, which is basically how quickly we can charge or discharge this energy storage. The first one is the volume. What I basically already described to you, if we double the volume, therefore we also double the amount of water we have, and this means we have more water at a high potential energy, and this means we can overall store more electricity or more energy, to be more general, in this kind of system. Then we have rho, the density of the liquid. Well, this is something which is pretty much hard to influence. Of course, you could use a higher density liquid in order to increase the energy you can store in this kind of system. But higher density liquids would, for example, be syrups or something like this. And they, of course, bear other disadvantages when it's about pumping them up or down. And also, it's a cost aspect, of course, that water is simply cheap and readily available. The next parameter being present in both of these terms here is the gravitational acceleration. This is also a parameter you, of course, cannot really change. This gravitational acceleration on Earth is 9.81 meters per second squared, so there's no way to optimize your system regarding this. The next parameter, which will only occur, of course, in the power term, is Q, so our flow rate. Basically, how quickly we're flowing water from the upper to the lower reservoir. Obviously, if we flow twice as much water from the upper to the lower reservoir, we will double our power because we will be able to run maybe another turbine, or our turbine will be bigger or something like this. Probably the most important term being present in the overall storage as well as the power term is delta H, so our effective drop height. Our effective drop height is basically defined as the upper level of the upper reservoir when it's totally filled, and the lower level of the upper reservoir divided by 2. So you will basically be at the average height of the upper reservoir. Because as it empties, of course, your effective height decreases. That's why you take the average. And from this, you deduce the height of the lower reservoir, because this is where the water will drop to. And this is a very much a key parameter, because this parameter now influences the stored energy as well as the provided power of the system.